inverter is fully installed. Now all we gotta do is turn it on. Did you know that 75% of you watching right now are not subscribed to my channel? That's bonkers. Engagement is what makes or breaks a YouTube channel, and I need your help. Subscribe today, and let's build a community together. Big fat nothing. Still got a lot of work to do then. On the last episode, we cleaned up and repaired this Applied Engineering ZRAM Ultra 2 card, but it's obviously still got problems with it. So let's get back to work. Well, this logic chip, the 74LS173, we know was bad. It was green and crusty, and I decided to test it, and it tested failed, so we replaced it. But we haven't tested the rest of these chips here, so let's go ahead and do that now. So you probably noticed that I did not test these two chips, these GAL chips. These are Lattice Semiconductor GAL chips for gated array logic or generic array logic or something like that. Basically, they're custom logic chips, analogous to a CLPD or FPGA or something of modern technology. These can be programmed kind of like a ROM can be programmed with different fuse settings so that when different inputs happen, they then set different outputs on the other side. They're basically little state machines, so you can replace a whole board of discrete logic with just these single chips. Now, why did I not test these? The reason being that these things can be locked by the manufacturer so that the fuse settings cannot be read back out. And our friends at Applied Engineering 30 years ago did that. So if I read these chips, I get nothing but all ones, meaning all of the fuses are not yet set. So how do we go about testing these chips? Well, I have an idea on that. What we do is we put them into another working card that I just so happen to have one of. Thank you again to Javier Rivera for sending me another card to test with. So we take these chips, we put it in this card, put this card in this machine and test it that way to see if these chips work. So let's do that now. Alright, so we have my GAL chips in a known working ZRAM board. So let's go ahead and turn it on and see what happens. We got a beep. We have a post screen, so that is very good. So I'm going to get this set up and kind of configured on the bench a little bit so that I can boot to the actual diagnostic test for this board to make sure it passes a complete diagnostic test to really give the gals a run for their money. Alright, everything's set up. Now let's run the test. Well, that's good. It passed the test. That tells me that the gals for my board are good, so I don't have to worry about them. So the next step is to put my board back together and then compare my board to the other board that I have and see what any differences are between them. Make sure my Bodge wires on the bottom of that board are in the correct spot. Make sure that all of the traces look good. And just to give it a full once-over and make sure I didn't miss anything. Looking at the differences between these boards, here's the known working board, and here's my board that's all messed up here. The big difference I see here is that my board has these odd little bodges here with this resistor going to, it looks like a ground pin or something, and this diode that flies off, and this I believe that's pin 40 of the CPU, which is like the reset pin? Weird? I don't know. And when we flip these over, I want to be careful because I don't have my pins protected here. Flip those over, and you look, you can see, yeah, there's no bodges up here going off to anything, but mine has those bodges. What is similar between both of these is that they both have this cross bodge here to the second pin of this gal. Mine's easier to see because it's blue, but on this one it's right here. So that bodge is the same. I also I use my continuity tester to test that to make sure it goes to the same pin, and it does. In addition, when you look right here, this trace here to this pin has been cut. And I again used my continuity tester on this one to see if that same trace is cut, and it is. When fixing this board as well, up here where this bodge was, I noticed that this trace here, this fat trace, was cut from this pin. On this one, it is not cut. So I'm thinking I'm going to have to solder bridge this over when I take this out to emulate this board exactly. So I'm going to go ahead and take these bodges out and modify this board, modify the broken board, so to speak, to more closely match the working board in operation. All right, bodge removal time. Let's get these wires desoldered. Okay, get them pulled out from underneath here. All this work I did to get these installed in here, and it turns out we probably don't need them, but you know, whatever. Okay. Carefully flip this over, and be careful again because I have my pins not supported by foam. The last thing I want to do is rip those out of there, and that would be bad mojo. Release that one. Pull it out. And we do the same here. Release that one. And pull it out. Okay. Flip it back over. And now we need to ensure I have a solder bridge between these pins up here. Or between this pin and this trace. Right there in the spot there. There we go. That looks bridged to... no, not quite yet. Hold on. Might have to put a piece of wire in there to bridge that. So we will do that. Just use a piece of this wire here from that previous bodge. Clean my iron a little bit. All we got to do is get it connected to there and there. There we are. Snip off the excess. Okay, so now I need to test continuity between that pin and something over here. So I've got my continuity tester there. Can't see it because I'm zoomed in, but you'll be able to hear it. It's working. So I want to test between the very bottom of this pin and right here. Yes, so that means that bridge is reconnected. Make sure I'm not connected between pins or anything like that. Nope. Everything is good there. So all we have to do now is put it back together and see if that fixed it. All right, time for another test. Let's see what happens. Big fat nothing. This board still has some sort of problem with it. Wow, that's interesting. It's actually changing as it runs. Play around here and see if I can get it to do something different. That's interesting. When I bend the board up, when I hold it down here and bend the board up in this corner, it does things differently. That is very odd. Okay, so I'm going to try something. Now, what happens if I bend up on this and then turn it on? Wow! It works if I do that. What happens if I let go? Does it freeze up? It looks like it freezes up. Interesting. So that leads me to believe that this board has a marginal trace somewhere on this side, again, where all the damage was. So let's take the board out. I'll take the board out, and I'm going to go over all of these solder points with my iron and some clean solder and just reflow the entire board, and we'll just see if we've got a loose solder joint somewhere. Spooky. You cheeky little bugger. Well, wouldn't you know it, the resistor right in this position right here, a 1500 ohm resistor that pulls up or pulls down a line on this gal chip right here, was faulty. When I was originally cleaning the board, I tested that resistor and it tested perfectly fine. But apparently it somehow died during the repopulation process of the board. It was while I was working on it and resoldering pins, it felt all loosey-goosey and weird in there, and then I went to test it, and it was something like 8 megohms, and that was wrong, and it's supposed to be 1.5K. So I went ahead and took the resistor out, and in the process, the leg of the resistor it fell off. So put a new resistor in there, and let's get it put in the board and see what happens. Awesome sauce. Let's get this thing booted up into the diagnostic test and run a RAM test and see what happens. Okay, we're running the Ultra 2, so we hit test number 4. Uh-oh, doesn't see any of the RAM. So we still have a bad trace somewhere, but we're at least making progress. Now the machine boots up, it can connect to the processor in the MMU and do all of the other switcheroo magic that the logic is doing, so that's good. But we've got some other bad traces, so let's keep digging into it. Who's the new guy? Well, let's fix that real quick. Sheesh. Okay, aside from that one pin that I found that I just didn't solder when I was putting all the sockets back in the board, found a couple other things wrong with this board, and I'll show you what I've done to diagnose and track that down. First things first, took my multimeter, and I took the known good board, which is hanging out all the way over here, and I created a list of mappings of what pins go where and what connects to what and all of that magic, to figure out what was supposed to go where. And I did that because there is no schematic for this board. It doesn't exist. So I had to kind of make my own quick pseudo-schematic. Did that, and then came back to this board and basically did the same set of tests on this board. And I found a couple of traces that were not connected. They're just broken, missing something on the board. After I did that, I actually plugged the unit in and turned it on, and then used my logic probe here to do some logic probe testing to ensure that the signals that I thought were broken actually were broken, and I did confirm that. So I'm going to actually get this all kind of situated with my logic probe, and I'm going to probe one of these broken pairs, and I'm going to show you what a broken trace with a logic probe sounds like. Alright, I have the board up and running here. This is powered on, and I have my logic probe here, right there, and I have it connected to the 5 volts and 0 volt rails here. And if I probe those, low tone for 0 volts, high tone for 5 volts. And then when it's picking up any sort of pulsing, you can hear it makes a specific sound. Now, here's one of the traces that are bad. I actually just probed it. This is pin 6 on the MMU. Pin 6 on the MMU goes to pin 5 on every single one of these chips, these RAM chips over here. So that means that if I probe this right here, and I get that sound, on pin 5 of all of these chips, if I probe it, I should get the exact same sound because they're all electrically connected. However, if I do that, and do this very carefully, you notice I'm getting nothing, or just kind of weird little clicky noises. And if I touch the probe, I get noise. That's because these pins, pin 5 on all of these chips, is completely disconnected and just floating in the breeze. There's no electrical connection between pin 6 and pin 5 over here like they should be. So that means somewhere in there that trace is bad. So I have a couple of traces to fix. I'm going to go ahead and fix those and show you what I did. So here are the two fixes I had to do to the board. Of course, the first one is the MMU to pin 5 connection that was screwed up. That pin 5 is address line 0 on all of the RAM, and those are all interconnected. But for some reason, between the RAM here and the actual pin, the trace, which I think is on the front side of the board and is like buried somewhere, I don't know. It's just busted. I can't even find where the trace goes. It just disappears somewhere. But whatever. I know it's supposed to be connected, so I went ahead and connected that. Over here as well, this is the data line, and it's supposed to connect a couple of these different banks together. It's like bank D and B, or D and A interconnect, or C and D, or whatever. But two of these banks basically share a data line. And for some reason, the trace on the top side of the board, again, that connects these two sections, even though it looks perfectly fine, it's not connected. And it was easier to run a Bodge on the back side of the board here, so I connected those two data lines together and did another test, and all the pins that are supposed to be connected are now connected. So next stop, put the board in the machine, test it again, see what happens. Here goes, full test. Awesome! Card passed. That is super cool. Now we need to get into checking the clock on this to make sure that that clock chip that I got works, and figuring out some way to get battery power to the board while the machine is off in a way that's not going to have a battery explode and destroy the Apple IIc or this board ever again. Okay, so I got the thing booted up here to the clock utilities by Applied Engineering, and I was able to set the date and time. As you can see, it's counting the time just fine. However, this wasn't the way it actually started. I've skipped ahead quite a bit, and I'm going to let you into a little bit of the behind the scenes of how I do some of my processes here. When I'm doing some of these repairs, I'll do a few steps of pseudo repair, a few steps of research, just to make sure that I'm on the right track when I'm doing the repair before I actually record it. I don't necessarily record every tiny little bit in piece of what I do, because some of these repairs can take several hours of research time, of testing, of whatever to figure it out, mostly due to my lack of skill and bumbling around like an idiot, but that's fine. So I was messing around a little bit with the clock on this, just to, again, get my bearings of how things worked. And again, because there's no schematic, I kind of have to figure it out on my own. And I found that on my board, my clock chip did not work at all, but the clock chip on the spare board did. During that process, I found that the oscillator, you can't see it, it's right over here, the actual oscillator crystal, the 32,768 Hertz oscillator crystal that is used as a timing reference, wasn't oscillating. So I'm like, okay, fine, whatever. With the chip out of this board and an oscillator that I stole out of this PC board that I keep around for spare parts. Always keep around junk boards and stuff to take for spare parts. You never know when you're going to need little things on the fly. Threw that in there, and then it stopped working again. it didn't work, and it was not booting up correctly. Basically, what was happening is with my chip originally, when you go to boot, it would crash after loading the clock driver. And when I switched to the one out of this board, it started working, but the clock wasn't running. Okay, fine, whatever. So, but after repairing that crystal on there, now with the clock chip out of this one, it wasn't working correctly. Weird. So two bad chips, whatever. So I swapped the chips back the other way, put my original chip in here, and it would boot now, but it would show weird random garbage up here on the clock, showing that the clock was running, but it would like randomly change the dates and times all over the place, then crash. Funky. So I swapped the boards around, and I swapped back between the spare board and my board and the different clock chips, and eventually it got to the point to where with my board and my clock chip it started working. I don't know why. No idea. So my normal process of trying to, just doing a little bit of learning in the background ended up me faffing about for about 3 hours until I got to this point. Lo and behold, I think it's fixed. I think what the actual issue is between these two chips is that the pins are they're kind of folded in too far or not far enough, and they're not really making good contact on the sockets or something like that. So they may need to have the pins splayed out a little bit for better contact. I think that's really all that was going on. During this process, I also found that the oscillator crystal in this board doesn't work at all. So when I send this back to Javier, he's going to have to replace his crystal. Or if he wants me to replace it, I'll replace it for him. I don't know, whatever. But back to my board. So it seems to be working perfectly fine now. Now I got to figure out a way to put a battery on it. I have a couple of ideas. First off, I've got, one of these aftermarket-y batteries, same voltage, same everything, and it's a nickel cadmium battery so that it can be charged when it's connected to the board here to keep its charge, in the same manner the original battery was, but I can keep it off board. I can throw it somewhere, run a wire to the outside of the machine, whatever, and put a socket on here so that if the battery ever leaks again, it's not going to destroy the machine. The other option is another little thing. I stole the battery socket out of that PC board. And this is a little 3-volt, CoinCell CR2032 battery that might also work in this with a combination of some diodes and stuff, so that when the Apple II is on, it's not trying to charge this battery. Some sort of sense circuit or something I might be able to bodge in there. I don't know. I haven't figured that part out yet, but when I figure out which way I'm going to do it, I'll show that to you, and that's going to be right about now. So here's what I came up with. I went with a standard coin cell holder. I happen to have it, and the holes in the board perfectly fit this through-hole coin cell holder. So it was almost like it was a predestination paradox that I would just put that in there and make that happen. But you can't just throw that in there, and the reason being is because this board is designed to charge the battery that's in there. And you can't really charge a coin cell. Probably won't blow up, but it might get hot and bad things will happen and the cell will fade or die too early and whatnot. So let's not do that. So I dug into the way this works, and I was thinking, well, the battery that's on here has to have some sort of diode to prevent it from trying to power backfeed the board while it's running. And I figured it out by tracing things out that basically this transistor right here is effectively used as a diode, more like a switch, but you can think of it as a diode is in this circuit, meaning this will switch on and provide 5-volt power in this direction, in towards the board, only while the board is on. It biases itself, basically. But when the board is off, it switches off, and then current can't flow back the other direction, and that way the battery here won't try to charge the board. So that's half of my circuit that I need, but I still need another diode. So we need a diode on the positive rail here to prevent it from receiving power back in this direction while the board is on, and so that's what I've done. If I flip the board over here, you can see I have a little black wire here, and if we zoom in and let it focus, basically what this is a standard germanium diode. It's a signal diode basically, but I just used it. It's fine. A diode to the between the battery and the actual positive rail, so that the battery can send voltage over when it needs to, but it's not going to receive voltage from the board while the board is powered on, and that basically solves the problem. So before I put this back in the board, I'm going to show you a quick diagram of how that's drawn up, how that works, so you can get a better idea of how that current flow works. Here's my JS CAD drawing. Sorry, Dave Jones, I'm stealing your idea of how this works. Basically, what you have is you're going to have two diodes pointing towards each other at a single point. And that means that no matter what, your circuit is going to get the 5 volts that it needs. Now, if the 5 volts is over here and it's coming from the external rail, it's going to be able to come through this way, go through this diode into your circuits, but it's not going to be able to go back through this other diode to charge the battery. The battery is set up exactly the same way in reverse. Basically, you got a diode pointing this way that's going to be able to come and provide voltage to the circuits, but it itself is not going to be able to provide, or it itself is not going to be able to receive voltage from the 5 volt while it's running, nor send voltage back the other way, again, because it's going to hit this diode, it's going to hit a big brick wall and not be able to do it. So basically these opposing diodes act as like half of a bridge rectifier and only allow voltage to come in towards this point and towards the circuits, but never cross over each diode. Okay, all that's left is to do a final test. We've got the working board in the machine with the battery. We've got the date and time set, and you can see the clock is ticking, and I have got a timer here. This is what I'm going to do. I'm going to get this clock running. I'm going to turn the machine off. We're going to run a time lapse. I'm going to run this thing for 10 minutes. 10 minutes on the time lapse. And at the end of that time lapse, I'm going to turn the computer back on, and we'll see if it's still got the right date and time. So let's do it. Okay, the time lapse is over. The machine's been off for 10 minutes. It's actually been a few more than 10 minutes because I did some video transfer from the camera here after the recording there. But yeah, so let's go ahead and turn it on and see if this battery kept the clock chip running and kept the time. Now, during this boot process, you're going to notice me hit a Control Open Apple Reset. That's because this machine, in combination with my floppy EMU and certain disk images, it doesn't boot all the way correctly the first time, and I have to give it the 3-finger salute. I don't know why. It's just the specific combination of this stuff. No trickery involved. It's just the way it is. Turn that on. I'm going to watch this. You can kind of see it there. It's going to go to idle, and then I have to control... Oops, didn't do it right. And now it'll boot correctly. I don't know why it does that. It just is. It's going to boot up. Clock driver installed. And did it keep the date and time? Ha ha! 29th November 2020, or in this case it probably thinks it's 1920. 23:25:47. I'm going to look at my clock over here and it says it's 11:26 p.m. So that is correct. Yes, I work late sometimes. So we got a working clock, a working card, working RAM. Everything is done. All that's left is to button the machine up, make it all pretty again. Well, that was super fun. We got both the clock and RAM function of this old card working again. I don't know about you, but there's something about fixing old broken cards that are hard to find and irreplaceable that just makes me super happy. If you're unaware, I do offer repair services. So if you've got a piece of retro computing hardware that's broken and you'd like to have it fixed, contact me. Thanks for hanging out with me today. Remember to like, subscribe, and ring the bell to stay up to date on my latest adventures. You can also support me through Patreon or by snagging some merch at jcm-1.com. Links in the description. Well, that's all for today's episode. While you're here, check out some of my other videos, and remember, 8 bits are all you need.